speaker. The next speaker will be Ling Ren, an assistant professor in computer science at University of Illinois. Prior to joining that university, he received a PhD from MIT and he worked as a postdoctoral researcher at VMware Research Group.
Thanks for the introduction. So today I'm again talking about analysis of Nakamoto consensus. So you might be wondering why yet another proof. Right? We already had 4 or 5 of these. And in fact, even this morning, the first talk was on exactly this topic. So my main motivation was to simplify the proof. Right? So Nakamoto consensus is this extremely simple protocol. I think it can be described in these 2 lines. The protocol is basically this, mine on the longest chain. And when you have a new longest chain, you send it to all. Right? And also you commit if you commit all the blocks that are buried deep. Right? But somehow it got this reputation that it's difficult to formally analyze, to rigorously prove that Nakamoto solves consensus. Right? And basically, I want to show you it should not have been that way. The analysis can also be quite simple. Okay. And just to give you a quick overview, I hope I can convince you this is nothing difficult. This is a simple result and simple proof. I'm going to show you that Nakamoto consensus, it solves consensus if this condition holds. It's a very short formula where alpha is the honest mining rate, beta is the malicious mining rate, and delta is the communication delay. Right? If alpha times this e raised to alpha delta is greater than beta, then the Nakamoto consensus protocol works. All right. So when I say it solves consensus, I'm using the traditional consensus properties, safety and liveness. Safety means all the honest nodes, they commit the same sequence of blocks. And the liveness means every transaction is eventually included in the sequence. Okay, so I want to claim this proof is simple, but we don't have a mathematical way to model simplicity. So bear with me. I have to use some hand-wavy metrics. Right? So this is the entire proof, about 2.5 pages. I think I could just let you read it. And will probably be done in 30 minutes, right? But well, it has to be a talk, so I'll walk you through it. And
the print is a bit small.
Yeah, the print is a bit small. Yeah.
So
I think I need 3 slides.
Before I start the proof, I would like to be clear on the statement. So because you said safety and liveness, but there are probabilities somewhere, right?
Yes. Yeah, they are safe and live with some probability, with overwhelming probability.
For both?
For both, yeah. Okay, and my proof builds on top of several amazing and inspiring works, including Raj Moha's talk from the morning. All right, let me just give you a quick overview of how this area evolved. All right, so the first groundbreaking work is Gray et al. It's GKL. It's the first rigorous proof for Nakamoto consensus. Before that, the analysis kind of went about ruling out particular attacks. Right? The Nakamoto himself did analysis assuming this is the best attack that can ever exist. He proves that attack would not work. Right? And the Gray et al. Paper is the first to rule out all possible attacks. So the only thing that's not nice about it is that it employs this what I call lockstep synchrony model, which is based in rounds. At the beginning of a round, everybody sends a message. At the end of the round, everybody receives the previous round message, and then we take our next action. Right? So in some sense, this means there's no communication delay in the network. Everybody always receives the message at the same time. And then you can see if we plug in delta equals 0, then the result I have degenerates to that case. Right. But even to show this result, I think they needed about 10 pages of proofs. Right. The next work is Pat, Simon, and Gillette. So they are the first to recognize the importance of introducing this delta delay. Right? And well, I didn't cheat. It's the default. All right, I'll comment on how I cheated in the end. All right. So their result is essentially this formula. It's also the honest mining rate needs to be multiplied with the discount. That's essentially the mining rate loss. Right. After the loss, if the honest is greater than the malicious mining rate, then Nakamoto consensus is secure, meaning safe and live. Right, to prove this result, they need about 16 pages. And it's easy to verify that this result is looser than what I'm going to show you. So next up is Raj Moha's paper, Kifo et al. So they introduced Markov chains to tighten up this result. Right? And their analysis is actually quite simple. It doesn't add any pages, so it's the same amount of complexity as the previous one. But the complexity kind of lies in somewhere else, that the end result is not so simple, not so nice. Right? So instead of having a few variables, they needed this quantity to be greater than beta, whereas these are from the Markov chain, the probability, the stationary distribution, and so on. Right? If we look at what those things are, this L00 and L10, they themselves are summation. And the summation has this one extra term that's a P sub I less than delta, which itself is another summation. Right. So it's I would say it's less of a it's a more complicated result in the end. Okay, so at some point I claimed.
So when they introduced delta, that's the transmission delay. Did they then assume a randomized scheduler or?
So it means every message, if it's from one honest to another honest, it arrives within delta time. But it can take anywhere between 0 and delta time. That can be decided by the adversary. So messages.
Over the delay, or
no, there's no probability distribution. The adversary can decide arbitrarily how much time it wants each message to take.
Okay, the adversary defines the function of the prefix then.
Defines
The function of the prefix.
the function of the prefix.
Message is it's a function that decides, given the prefix, which message is delivered next.
Sure, yeah, the adversary can control that in any way he likes. I'm not requiring the adversary to explicitly state how he wants to do that.
Okay.
All right. So I thought my result is tighter than that, but I think I have to take that claim, because there's a recent paper by Zhao that shows this summation, 3 nested summation, is actually exactly the same as the formula I have there. Right? And to show that, they need another 13 pages and 127 equations. Right? Uh-huh.
It's exactly the same.
They claim it's exactly the same. I haven't verified. But I kind of believe that, because in the end, fundamentally, the approach are very similar, and they should not give different results.
I thought the point of the bottommost, rightmost thing, this thing, was that you could analyze a bunch of similar situations with the same ideas.
Yes, that is still there. So Markov chain is still useful for that. So all I'm saying is, if you want to give a proof to Nakamoto or to Ghost, we do not have to rely on Markov chain. But Raj also did analyze the best attacks, right, to show how successful best attacks can be. That I do not claim I have any better analysis. All right. So now let me jump into this proof. So I also need to first define the model, and Raj kind of did most of that for me. So the first assumption we have to make is that there is a known message delay bound. So that's the standard synchrony assumption. But a couple of comments. So Bitcoin, Nakamoto runs in a peer-to-peer network. Right? For the sake of my analysis, I'm assuming point-to-point connection. Right? But if you insist on having a peer-to-peer network, we can still make that work. It's just that this delta should take into account all the different hops in the network. Right? So delta is the upper bound for a message to travel through all hops in the network. Okay. So next thing, I think the audience already asked, the adversary controls message delays within 0 to delta. Right? It has freedom to delay each message anytime in that range, but it cannot delay a message more than delta. Okay. So third, this is a quick comment. So this model is exactly the same as in the PSS and Kiefer paper, but they call it other things. They call it asynchrony or partial synchrony. I personally felt that's a misnomer, and I'm glad that Raj agreed with me. So I would call this model non-lockstep synchrony. It is synchrony because we have a message delay bound. Partial synchrony and we have a known message delay bound, delta. Partial synchrony and asynchrony means either we have no bound or we have a bound but no one knows about it. Right? So those are harder models to deal with.
So why can't we just think of it as continuous time?
I am thinking about the continuous time. I don't have any rounds. That's the, I want to emphasize here, my model doesn't use rounds. Right? So it's, whenever I receive a message, I'm going to take the next action immediately. I don't have to wait till prescribed rounds. So in fact, in the previous models, they also, rounds to me is more of an artifact, because they want the rounds to be infinitely small. So essentially, it is the continuous time model. But I think it may simplify some of their analysis. That's why they introduced the round. Okay, so yeah, on that, the next assumption is that I assume mining is this ideal memoryless event, which basically means it's a Poisson process. And I'll use alpha and beta to denote the collective honest mining rate and the collective malicious mining rate. Right? Basically, honest nodes collectively will mine alpha blocks in unit amount of time. Right? In some sense, maybe alpha is 0.6 block per 10 minutes, and beta is a 0.4 block per 10 minutes, roughly speaking. Okay, so lastly, one more ideal assumption. I assume alpha and beta do not change. They stay the same throughout the protocol. Right? So this is not really what's happening, because in Bitcoin, people come and go. So the mining rate fluctuates a little bit. And every 2 weeks, it's adjusted to the 10-minute mark. Right? But essentially, I'm assuming here the difficulty adjustment mechanism is perfect. It takes effect in real time.
But perfect means alpha plus beta doesn't change, right? But you're assuming alpha and beta individually don't change, so it's a stronger assumption than that.
I see. I did not have to do it that way. I can assume, say, lambda, which is the total network mining rate, does not change, and alpha and beta are two fractions, and as long as they satisfy that equation. Yeah. But yeah, good catch. I could have made it slightly weaker.
I don't really understand what you mean by this Poisson process and mining rates. Like when you deal with continuous time, what does the protocol mean?
The protocol is I got a block, then I start mining. I will compute hashes using whatever rate I can. Right? Whenever I manage to find the next block, extending the previous one, then I announce the block.
But yeah, then you're assuming the attacker is following the protocol honestly, or?
No, of course not. The attacker will do whatever he wants to do.
But the word mining, it's not something that exists for an attacker, right? It's an algorithm as well.
Mining is, at any time, I'm working on the longest chain I know, for honest. For malicious, at any time, it can try to extend from anywhere it likes. But all it tries to do is to find a block that extends somewhere from the chain.
So time is continuous, right?
Yeah.
And how do you model it exactly? So it's like every machine should be aware of the current time, right? If time is a real number. Then
No, I believe the Nakamoto protocol really doesn't need to use time. Right? All I'm doing is I'm trying to compute hashes as fast as I can. And whenever I find a block, I'm going to announce it to the world.
But this is a much more idealized model than what we did in PSS.
No, I disagree. I think it's actually a less idealized model than the run.
The only thing you're doing is trying to extend the block running the protocol.
Yeah. The bad guys can mine a block and hide it, right, and send it at some later time. The bad guys may not extend the longest chain. It may attend somewhere in the middle. Right? All of the things it can do in your model, I'm also adopting. Right? It's really no difference because you also want your tiny rounds to be really, really tiny, right? To be infinitely small. Right? When you take it infinitely small, it's exactly the same model as I have here.
I guess I don't see it because it's very different to assume you have an idealized object like a random oracle, right?
Yeah, let me comment on that later. Yeah. All right. Oh, by the way, I'm also assuming there's only honest and versus malicious, no rational behavior. That is a big part in Bitcoin, but all of our analysis do not tackle that for now. Right, so some preliminary chain of bound. I think everybody knows that. Right, so if for a sum of independent Boolean random variables, it cannot deviate too much from its mean. Right, and then there's a very similar bound for a Poisson process. If a Poisson distribution has a mean of lambda t, then it also cannot deviate too much from that mean. Right, this should be natural because the Poisson is basically an infinite summation of Bernoulli variables. Right? So it's as expected. All right, so key idea of the proof is essentially the same. We're trying to count the number of useful blocks, and we'll show that the number of useful honest blocks is more than the number of maliciously mined blocks. Right, so what I mean by that, I'm going to put all the honest blocks on the time axis based on when they are produced, when they are mined. Right, we hope they form a chain. For now, let's assume there are no malicious person. Right? I'm trying to define things. But occasionally, it's not that good situation. Occasionally, two honest mined blocks will extend the same block. Right? Why did that happen? It's because they are mined too close to each other. Right? So this latter block was not aware of the first block. Right? So in particular, how close is too close? It's within delta. Right? If it's more than delta, then the latter block was aware of the previous block, and then it will be building on top of it. Right? So if two blocks are mined too close to each other, then one of them will be wasted. Okay, so let's formally define that notion. I'm going to define an honest block mined at time t is called a non-tailgater if no other block is mined within the delta time before it. Okay. Otherwise, it's a tailgater. So then this is a tailgater, and the other blocks are non-tailgaters. Right. And we know that the inter-arrival, meaning these gaps, for a Poisson process follow independent exponential distributions. Right, so the probability that any of these is non-tailgater is e raised to alpha delta. That's the term that shows up in the end. Right, and they are independent. Okay, so I'm going to call this quantity g because it's shorter. Now, lastly, I'm also defining another notion called a loner. It is a block. If a block is not mined, if no block is mined delta before it and no block is mined delta after it, then it is called a loner. Right? It's far away from everybody. Right? On this figure, these two blocks, those two purple blocks are loners. This one is not, right? Because even though it does not tailgate the previous one, it is tailgated by the next block. Okay. So these useful blocks, they have some nice properties. In particular, non-tailgaters, they do not have the same heights. And the loner does not share height with any other honest block. Right? And the proof is very simple. It suffices to show that if two blocks do not tailgate one another, then they will not be on the same height. Because the latter one is aware of the previous one, so at least the latter one will be attempted at a higher height. Okay. So next, we're going to show there are many of these useful blocks. In particular, in a time interval of duration t, there will be, roughly speaking, g alpha t non-tailgaters and g square alpha t loners, except for small probabilities. Right. By the way, I should mention loner is the convergence opportunity defined by the PSS paper and in Raj's talk. Right? And the Markov chain Raj introduced is basically to count the number of loners. Right? And I'm going to show you a simpler way to count the number of loners. Okay, so let's do the first part first. So in this duration of time t, I'll use n to denote the number of honest blocks mined. So n follows a Poisson distribution. Because of our Poisson tail bound, it's at least 1 minus half delta alpha t, except for small probabilities. Right? We also said each honest block is a non-tailgater with a probability g, which is e raised to minus alpha delta. Right? So then using a Chernoff, it's at least 1 minus half delta g times n, plug it in. It's what we have. Okay, so next, let's count the number of loners. It's almost the same. There are n number of honest blocks. And the number of loners is basically that summation of Boolean random variables. Each loner has a g square probability. Each block has a g square probability of being a loner because it has to be a non-tailgater, and the blocks next to it, after it, it also has to be a non-tailgater. But the only complication is that we cannot use Chernoff bound because these things are actually dependent because they share this variable. Right? So luckily, yi and yi plus 2 are independent because they are derived from independent exponential distributions. Therefore, we can break up this summation into two parts, even and odd, and we invoke Chernoff separately on both parts, and we will get the results.
Does that not mean that you're underestimating the number of your loners?
No, I think we can show this is tight. Using the Markov chain argument, this is actually tight. All right. So yeah, quick summary. Non-tailgaters do not share height with other non-tailgaters, and there are that many of them. Loners do not share height with any other honest blocks, and there are this many of them. Right? I need to go a bit faster on time. So liveness. Right, liveness traditionally is broken up into two parts, chain growth and chain quality. Growth says at time t, the chain is at least this long, and quantity says among those blocks, some fraction of them are honest. Right? Chain growth directly follows from the properties of non-tailgaters. Because non-tailgaters have different heights, so the chain length is at least as long as the number of non-tailgaters, which is what we have, what we just shown. Right, quality, so chain length is at least, roughly speaking, g alpha t. And the worst case is that all the malicious blocks make it into the longest chain. That's when the honest fraction is the smallest, which is this quantity. Right. I'm using delta over 3 here because it turns out 1 plus delta over 3 divided by 1 minus delta over 3 is less than 1 plus delta. Okay, so lastly, safety. So safety statement says if we commit by waiting until blocks are buried by k deep, that commit rule will be correct except for exponential in k probability. Okay, so that's the hardest proof. So, okay, I don't have time to go through this carefully, but essentially this is the situation we're analyzing. It's also in the GKL paper, right? If we violate safety, at some point we need to have two diverging chains that are length k or longer. Right? I'm going to call B prime 0 to be their last common ancestor and B0 to be their last honest common ancestor. So I'm going to mark their heights and when they are mined. Then I'm defining Y to be the set of all loners that are mined within this period. I'm defining Z to be all the malicious blocks mined within this period. Right, now we can show a contradiction that z should be at least y, but also z cannot be larger than y. For the first part, we just need to pair every loner with a malicious block. Right, the way we do it is the following. If a loner is like in this region, then we can pair it with this block. By definition, that is the last honest ancestor, so all of these blocks are malicious. Right, so that is z is a malicious block. If y is over here, then we'll pair it with the corresponding block on the diverging chain, because I showed you loners do not share height with other honest blocks, so this pair I find must be a malicious block. Right, so every loner is paired to a malicious block, therefore z is at least as large as y. On the other hand, we said the rate at which honest miners can produce loners is faster than the rate at which malicious miners can find blocks. Right, so therefore, it's actually very straightforward that y should be larger than z. Right, so roughly speaking, y should be g squared alpha t, where z is beta t. Right, when we are waiting for blocks to be buried deep, t minus 2 delta is roughly speaking t. Right, so intuitively, our safety condition says exactly that. Okay, do a little more steps. It's also very simple. All right, so lastly, to avoid this contradiction, some unlikely events regarding the tail needs to happen, and that is the probability that Nakamoto loses safety. Right, and all of those events happen with the e raised to delta square beta t. Right, but we want the probability to be expressed in k. Right, and so that's the last catch. We need to show that t is at least linear in k. Right, what is t? T is the time to find k blocks in a chain, which is the summation of k IID exponential distributions, which is an Erlang distribution. If you plug into its cumulative density function, we can show that k times beta is at least k.
So here, why not 2 times k? Because you have 2 diverging chains, right?
So you're saying maybe it could have been tighter?
Yeah, tighter. This is my point.
Yeah, possible, yeah. All right, so yeah, that's the end. To summarize, Nakamoto solves consensus if this condition holds. This is not known to be tight because our best attack works only when G alpha is less than delta. So there is a gap there. I personally felt it's our proof is not tight. The attack is indeed the best attack. I'll end there.
I try to understand how the adversary comes in the picture, how sort of the delaying of messages influences the probabilities.
Right, so I'm not showing you how the attacker plays a role here, right? Which actually should be the case because this proof holds for any adversarial behavior. So basically, the best attack we have is the adversary mines its own chain and delay every honest block to delta, right? Then every tailgater from the honest will be an orphan block. Right? So the honest chain will grow at the rate of a non-tailgater, which is G alpha. Right? If the bad guy has a higher mining rate than that, then the bad guy's private chain will outgrow the honest node.
So I like the general approach in order to get a good bound, but I also am very worried about the general approach of just saying that you can abstract away what the attacker is doing. So assume, for instance, that Nakamoto's protocol had a property that you can take one block and maul it into another block that was also accepting.
You can take a block and
maul it into another block that is also a valid block.
What do you mean by maul it?
I can take one block and maybe change it a little bit, and that will also be a valid block.
You mean that's a bug on Bitcoin?
Let's assume that was the case.
Okay,
right?
okay.
If that was the case, your analysis still goes through, right? You're just assuming
Yes.
mining, right?
Yes.
But it goes through for a protocol that's broken. So there is nothing in your analysis that
Sure.
provides these type of things.
Sure.
And that is why it's very important actually to analyze the protocol, considering a PPT attack. And this is, the classic tradition in cryptography, that we make some maybe assumption about the primitive, maybe assume random oracle if we want to deal about with time.
Can I say something?
Only assuming that you have restricting the attacker to extending blocks is dangerous.
But if there is a bug like this, it costs nothing to mine for the guy who knows how to exploit the bug.
But how do you prove
So it's not true.
Right.
So the argument doesn't say anything in this case.
That's not my responsibility, right? If your protocol,
right? So if you want to analyze a protocol, you need to prove that there are no such attacks also, and that is missing in your analysis.
so all I'm claiming is if your protocol's mining is secure, then this analysis applies. Of course.
A proof of security should also argue that mining is secure somehow, right?
No, but it's okay. He's proving a model, and then if you want, you can prove something more realistic. There's no problem.
That is the difference between this type of analysis and the previous analysis,
totally.
right?
It's a
So
different.
it's a simplified model because it doesn't prove these attacks.
Yeah, I'm out of time, but I'm happy to discuss why I think this model captures the essence.
No problem.
Are we going to have a discussion about models versus reality?
Depends on whether the chair allows it.
Yeah, I think we're out of time. So.
All right. So I'll introduce the next speaker.